Hello ladies and gentlemen, this will be a first video in a series of videos on the concept of heat transfer. This is mainly intended for undergraduate chemical engineers who have had some exposure to transport phenomena, specifically mass and momentum transfer. So we'll start this introductory video on heat transfer by answering two questions. First, one question is, what is the difference between heat transfer and thermodynamics? The other question is, what are the ways in which heat can transfer itself? So let's start with the first question. What is the difference between heat transfer and thermodynamics? And we can put it this way. The concept of energy is used in thermodynamics to specify the state of a system. It's also known that energy can be neither created nor destroyed, but only change from one form to another. So, in retrospect, the science of thermodynamics deals with the relationship between heat and other forms of energy, but the science of heat transfer is concerned with the analysis of the rate of heat transfer taking place in a system. The energy transfer by heat flow can't be measured directly, but it has physical meaning since it's related to a measurable quantity called temperature. And that's all we'll leave the first question to. So the second question, what are the ways in which heat can transfer itself? Or what are the modes through which heat can transfer? So there are three different modes in which it can transfer. They are known as conduction, convection, and radiation. So throughout the remainder of this video, we'll actually go through each of these modes of heat transfer. So let's start off with conduction. Conduction is defined as follows. Conduction is the mode of heat transfer in which energy exchange takes place from the region of high temperature to the region of low temperature by kinetic motion or direct impact of molecules. So let's try to put this in perspective by looking at an example of two objects that are in a head-on collision with one another. So before collision, let's consider the following two objects. Let's say we have a green ball at a temperature T1 and a blue ball at a temperature T2. And these two objects are on a head-on collision with each other. And let's just say, for the sake of this example, that temperature T1 is greater than T2. So, what do we get out of this? Well, we can tell what's going to happen during a collision between these two objects. So, what's going to happen during a collision? Well, for one thing, the green object will be in contact with the blue object. And during the time in which these two objects are in contact with each other, there will be a heat transfer between them. So let's zoom in on the point of contact between the green ball and the blue ball. So when the green ball and the blue ball are in contact with each other, we should observe and note that heat transfers from the green ball to the blue ball, and we call that heat Q, in this picture at least. So and this makes sense according to our definition for conduction, where we say that heat is transferring from a region of high temperature to the region of low temperature by direct impact of the molecules. So that makes sense according to this definition. So let's just note that down and actually write it out. So we note that a heat Q is transferred between the two objects only when they are in contact with each other by conduction. So keyword here is contact. So now let's just keep going with this example and let's look at what happens after the collision between these two objects. So after collision, we will note that the green ball will be at a temperature T1 prime and the blue ball will be at a temperature T2 prime. These are the new temperatures of each of these objects as they go their separate ways. So what we'll notice though is that T1 prime must be less than T1 and T2 prime will be greater than T2. This makes sense according to our definition of conduction, because if the green ball was the region of high temperature and the blue ball was the region of lower temperature, it makes sense that the new temperature of the green ball will be less than its original temperature. Likewise, if the blue ball is the region of low temperature and it's the one gaining heat, then it makes sense that the new temperature of the blue ball is greater than it was before the collision. So, another interesting point to mention over here is, let's ask ourselves, does T1 prime and T2 prime equal each other? Does this system actually reach thermal equilibrium? Well, the answer to that is no. Or rather, more precisely, it's not necessarily. It all depends upon how long those two objects are in contact with each other. So let's recall, let me get a better color than that. So let's recall Newton's second law, where force is equal to the time rate change of momentum. We can actually rearrange this and say that the change in time is approximately equal to the change in momentum divided by the force that the two objects hit each other with. So this time over here is the time that the two molecules are, or the two objects rather, are in contact with each other. So what is the total heat transferred between the two objects? Well, instead of defining Q, we usually define Q to be Q dot, or something called a heat transfer rate. Because once we know the heat transfer rate, which is in units of joules per second, we can multiply that by time and determine the total heat that was transferred between the two objects. So let's summarize this and just go back to the definition for conduction. So on a molecular level, conduction has to do with molecules within a system or within some object, where those molecules impart a transfer of heat between each other by being in contact. So basically, conduction is heat transfer within a medium. For example, Like the water molecules in an ice cube, they can hit each other back and forth in a solid, and they vibrate a lot. Hence, they're transferring heat between each other. Same thing applies to a liquid. Likewise, the same thing applies to a gas. The only thing that changes from phase to phase is the probability that two molecules will hit each other, come in contact, and transfer heat. So as an exercise for yourself, you might want to think about, okay, how much heat would transfer between air versus a liquid versus a solid? And you'll see that chances are the best way to transfer heat are through a solid, since the molecules are so closely packed together. So molecules in a solid don't have to travel far in order to hit another molecule and then to transfer heat, unlike the case with a gas, where there's lots of space between the molecules. So that's it for conduction. So let's move on and talk about convection. So let's talk about convection. So, reading the definition, convection occurs when a fluid flows over a solid body or inside a channel while temperatures of the fluid and the solid surface takes place as a consequence of the motion of fluid relative to the surface. So, key thing to note here is, when it says fluid, this doesn't necessarily imply just a liquid. A gas can also qualify as a fluid. Furthermore, that fluid doesn't necessarily have to flow over a solid. It could be another immiscible fluid, such as an immiscible liquid on top of another immiscible liquid. So, a key thing to realize here is that it doesn't matter what temperature the solid body is, or the fluid, or whatever two distinct phases are in contact with each other, the result is heat transfer occurs as a consequence of the motion of fluid relative to the surface. So that is key. So from this, we actually find that there are other modes by which convection itself can occur. So we'll look at these convection modes in a bit, but basically convection, what sets it apart from conduction, is that convection is heat transfer between distinct phases. So now let's look at convection modes. So there are two different modes by which heat can transfer through convection. One is through free or natural convection. The other one is through forced convection. So let's take a look at free convection for the time being. So in free convection, let's say we have a hot solid green object, and this, just to note, this hot solid green object doesn't have to be hot. It could also be cold relative to some free flowing cold molecules. So these little individual blue molecules that you see here, all of these blue molecules, each of them pretty much have random direction in which they're moving. So they're all governed by turbulent flow. So at some point in time, one of these blue molecules is bound to come in contact with the hot green surface, and as a result transfer heat for whatever time those two objects are in contact with each other. So let's turn our attention now over to forced convection. So in forced convection, we have a different scenario. In forced convection, the blue molecules can actually be moving in accordance with some driving force, according to the boundary layer theory that you may have learned about in mass or momentum transfer. In either case, these blue molecules are actually moving with some velocity, either in a turbulent flow or laminar flow. Let's just consider, for argument's sake, that it's all laminar flow. So all of these blue molecules are actually flowing over the hot green surface. And more of these blue molecules are in contact with the hot green surface and transferring heat. So one would be inclined to say that the heat transfer rate in forced convection is greater than that of free convection. However, that's a mistake, because although more of these blue molecules are in contact with the surface, you have to remember all of these molecules, these blue molecules, are being forced to move in a set direction. So the time in which each of these molecules are in contact with the hot green surface is dictated by how fast each lamina of blue molecules are moving over the surface. For example, if these blue molecules are moving really quickly over the hot green surface, then the time for heat transfer between the blue molecules and the hot green surface is very, very small. Hence, the heat transfer between the blue molecules and the hot green object is very, very small. But we can also change the flow such that each of these blue molecules are in contact with the hot green surface for a longer period of time by forcing the blue molecules to move slower. As a result, the blue molecules are in contact with the hot green surface for a longer period of time, which would then increase the total heat that is transferred between the green phase or the solid phase and the fluid phase, the blue molecules. So that's sort of the difference between forced convection and free convection. So just remember that what separates convection from conduction is not necessarily that the mechanism by which heat is transferring, because that remains the same, where the condition is molecules have to be in contact with each other. But rather, what makes it distinct from conduction is that heat is being transferred between two or more distinct phases. So, with that in mind, let's move on to radiation. So now, looking at radiation, the last mode by which heat can transfer, let's look at the definition as follows. So, radiation occurs when two bodies at different temperatures are separated by a perfect vacuum. Heat transfer between them by conduction is not possible. In such situations, heat transfer between the bodies takes place by thermal radiation. That is, the radiative energy emitted by a body because of its temperature is transmitted in the form of electromagnetic waves, according to Maxwell's classic electromagnetic wave theory, or in the form of discrete photons, according to Planck's hypothesis. So basically, instead of tangible molecules actually coming in contact with each other to transfer heat, the mechanism is completely different. Instead, we have electromagnetic waves actually transmitting energy. One biggest example of this is the sun and the earth. So, sorry, forgot to color some continent green. And, well, let's leave that as Antarctica. So, here we have the sun and the earth. The earth is bombarded by solar radiation from the sun. which is also the cause for all autotrophic life to live, and hence us as well. So, the energy emitted by the sun comes from the fact that two hydrogen atoms impact each other with such a force that they actually form a helium atom. However, the sum of the mass of a helium atom doesn't quite equivocate to the sum of the masses of two hydrogen atoms. So, where did the leftover mass go? Well, it comes from E is equal to mc squared, although technically the full rule is energy squared is equal to momentum squared times the speed of light squared plus the mass squared times the speed of light to the fourth power. This is the mass-energy-momentum relationship, as formulated by the one and only Einstein. As a result, from this, we can explain that the leftover mass actually converted itself to energy, which is also the cause for solar radiation by the sun. Another way in which we can get energy in the form of radiation is through looking at the simplified Bohr model of the hydrogen atom. Whenever we see an electron move from a higher orbital shell to a lower orbital shell, we see that it gives off some energy, because its energy is the energy of an electron is associated with which energy level or shell it is in. However, of course, for that high energy electron to lose some energy, we have to conserve energy somehow. Well, that is not always the case, as we'll see in some quantum mechanical models. However, for the purpose of basic heat transfer, we are restricting our conversation strictly to the classical concepts of heat and energy. But, so for the next part, you can you can not pay attention. It's just me trying to give you more insight into what's happening. So let's say we take a quantum mechanical model over here. Suppose we have over here an atom in an excited state where we have an electron in some high orbit over here, high level shell, and then we have an incident photon that comes, hits this electron, and forces it to go down to a lower energy level. As a result, when that happens, not only does that incident photon leave, but the energy that the electron previously had, by moving to a lower energy orbit or shell, emits another photon. So, you got one photon that was emitted here, and as a result ended up with two photons emitted after. So that's another way in which electromagnetic waves or radiation can be developed. Now, just to conclude this whole segment, this whole video, bear in mind it's not necessary that radiation, conduction, and convection all happen indistinct and independent of one another. It can be the case that convection and radiation simultaneously happen. Or it could also be the case such that conduction and convection simultaneously occur. Or it can also be the case that all three simultaneously occur, or any combination thereof of the modes of heat transfer that can occur. So that concludes this introductory video on heat transfer.